Hello, everyone. I'm Linsong. I'm going to talk about the benefits and limitations of user interrupts for the user space preemptive scheduling. This is joint work with Daniel, Tao, and Amy. Today, tail latencies are expected in the microsecond scale. One reason is that many user requests are funneled out into smaller tasks, so the slowest task will dominate the response time. Another common case is a data-dependent workflow. A user request can involve multiple tasks with data dependency. The response time is essentially the sum of all of the task latencies. So in both cases, the latency of a single task needs to be as low as in microsecond scale. However, this is not always achieved today. One reason is the variability in service time. Variability is natural in practice, as service time can depend on task type, size, and input. This is very common in microservice, web servers, and database applications. So when these tasks run together, short tasks suffer from the problem of head-of-line blocking. For example, in the scheduled run queue, these short tasks are blocked by the long task. Consider a long task can take hundreds of microseconds or even milliseconds. This short task will miss a microsecond listening target. This is a fundamental problem because of variability in service time. For example, in the database application, the short transactional job can be delayed by a long analytical job. So to address head-of-line blocking, one common approach is to add more cores. So in this case, we add 2 more cores. This short task can be processed earlier than before. However, this will waste CPU resource, which is not an efficient approach. Another approach is by preemption. Preemption is not new in schedulers. However, most schedulers use millisecond level preemption. This can't address head-of-line blocking in microsecond scale. Instead, we need fine-grained preemption, which is in microsecond scale. Specifically, we can preempt the long task so that the short task can get a chance to run. In this work, we will try to use fine-grained preemption to handle head-of-line blocking. However, existing preemption mechanisms have significant limitation. One approach is by compiler instrumentation. The compiler inserts this piece of code throughout a user program. Then the user program checks if it should yield or not. The Go language runtime uses compiler instrumentation. The Go developer found that when instrumenting as loops, this slows down the program by 7% on average, but up to 90%. Volume time also suffers from the high overhead. Another mechanism uses signals. It uses a timer call to send a signal to preempt the running threads. However, the problem is that receiving a signal is very expensive because of the involvement of kernel space. Now, fortunately, a new hardware feature, user interrupts, can bypass the kernel. They are available in recent Intel CPU. Our measurement shows that receiving a user interrupt has significantly lower overhead because of the kernel bypass. So in this talk, our main question is, can user interrupts help achieve fine-grained preemption compared to existing preemption mechanism? Are there any trade-off between this mechanism? Does this new hardware feature have any limitation? To answer this question, we first have a macro benchmark study to understand the basic overhead of the different preemption mechanisms. We also built 2 user-level preemptive scheduler using user interrupts. This would enable us to evaluate the overall performance of the preemption mechanism when they are working in the software stack. So I will talk about the design and the studies in this presentation. In our macro benchmark study, we preempt benchmark programs with the 3 preemption mechanisms: signal, user interrupts, and compiler instrumentation. The compiler instrumentation is implemented with Concord. The metric we used is the runtime slowdown compared to non-preemptive execution. This reflects the overhead produced by each preemption mechanism. First, let's compare signal and user interrupts. The x-axis is the preemption quantum, which means the preemption interval. So the preemption becomes finer-grained from left to right. The y-axis is the slowdown of program. Our first observation is that user interrupts have significantly lower overhead than signal. This is not surprising to us. The comparison between user interrupts and compiler instrumentation is more complicated. With larger quantum, compiler instrumentation tends to have higher overhead. Look at the code instrumented by the compiler. The program needs to put the shared variable at all instrumentation points, even though the preemption rarely occurs at a large quantum. In contrast, when using user interrupts, we only need to pay the overhead when the preemption actually occurs. However, with smaller quantum, the conclusion is a little different. Compiler instrumentation has lower overhead. That's because pooling becomes more efficient than before, as preemption is more likely to occur with smaller quantum. Note that both of the large and small quantum are in the microsecond level. Overall, there is a trade-off between user interrupts and compiler instrumentation. Even though the trade-off, the compiler instrumentation has another limitation. The overhead can be very high in some cases, such as test loops. In the program a matrix multiply, there is a 25% of slowdown. People instruments at loops to make sure you can preempt all of the control flow. But test loop end up checking the shared variable very frequently. This raises a question: where should the compiler instrument? For test loops, loop unrolling can sometimes reduce polling overhead. However, it's still challenging to decide a good depth for loop unrolling. That's because excessive loop unrolling can even make program run much slower because of the increased instruction cache pressure. Instrumenting at function call can also be expensive, especially for short functions. Overall, we observed a non-trivial configuration space that require manual intervention, and all of the configuration will change with different input. In summary, signal always have high overhead. When comparing between user interrupts and compiler instrumentation, there is no perfect approach. The compiler approach may have lower overhead with smaller quantum. However, the overhead will be significantly high at some cases. In contrast, user interrupts have consistent and predictable overhead. Also, user interrupts also have improved usability since there is nothing to configure. We built two user-level schedulers with fine-grained preemption using user interrupts. Aspen KB is built on a highly optimized kernel bypass runtime. This highly optimized kernel bypass runtime will fully realize the benefits of user interrupts, as they have very low software overhead. Aspen Go is built on the popular Go language runtime. This represents a more real-world and common used environment. This shows the main components of Aspen KB. We have several application cores. Each core has its own run queue managed by the scheduler. Each core also has a receive queue in the network stack. There is also a dedicated timer core, which preempts the application cores. The timer core is a common design in the preemptive system. Since this is critical to the fine-grained preemption, we still have the timer core. Existing scheduler preempt application core periodically. For example, Linux scheduler sends preemption every few milliseconds. However, when preemption is in the microsecond level, the periodic preemption will be extremely expensive. Even though user interrupts have lower overhead, they are still not free. So our policy is to preempt only when necessary. If there are no more urgent tasks waiting, there is no need to preempt the currently running task. Specifically, the timer core periodically checks the network stack and the scheduler run queue. If the timer core finds any task waiting, it sends a user interrupt to preempt the currently running task. Otherwise, it avoids the preemption. So with this approach, Aspen KB can avoid over 70% of preemption events, which significantly reduce preemption cost. To reduce head-of-line blocking, another policy is to prioritize short tasks using a two-queue scheduling policy. In addition to the run queue, we add a separate queue for the preempted task. Once the task is preempted, that's moved into the preempted queue. As a result, long tasks eventually accumulate in the preempted queue. Overall, this prevents a newly arriving task being blocked in the scheduler run queue. However, the new task can still be blocked in the network stack, just because existing schedulers don't pull the network stack frequently. They either have a background thread pulling the new packets, or only pull them when the scheduled run queue is empty. As a result, even with preemption, newly arriving tasks are still blocked in the network stack. Our solution is to match the polling frequency with preemption frequency. Specifically, the application call pull the network stack on each preemption. When the application calls are preempted, they pull the network stack and move any available task into the run queue. The frequent polling does have a high cost because of the kernel bypass network. Overall, AspenKB enables fine-grained preemption. We also added fine-grained preemption to the popular Go language runtime. Our principle is to not overhaul the Go runtime, but make minimal and realistic change. Under this principle, some design from AspenKB can be adopted in AspenGo unless significant change. For example, Go only pulls the network stack when the scheduled run queue is empty, so the new tasks are still blocked in the network stack. AspenKB addresses this by polling frequently. However, AspenGo can't do this because frequent polling the Linux network stack is very expensive. Instead, AspenGo offloads the frequent polling to the timer call. Because of this, AspenGo is still less effective at handling head-of-line blocking. Also, because AspenGo can't check the expensive network stack frequently, it is unable to avoid unnecessary preemption. Finally, Go has high context switch overhead. This is hard to address as the schedule logic is fundamental in the Go runtime. This makes Go have a high preemption cost in software. The new hardware feature user interrupt can't help on that. Overall, AspenGo suffers from these limitations, which can be addressed easily without a significant change or even an overhaul to the runtime. To evaluate the performance of the three preemption mechanisms in application, we implement all of the three preemption mechanisms in AspenGo and AspenKB. In our experiments, we run a load generator in the client and the application with Aspen in the server. The first application we run is data frames. The task has variable service time ranging from a few microseconds to hundreds of microseconds. This figure shows the result of a short task and one long task. The x-axis is the load. The y-axis is the tail latency. Lower is better. Among all of the preemption mechanisms, user interrupts achieve the best throughput, with 30% higher throughput than non-preemptive execution by preempting long task. Since we are preempting long task, AspenKB sacrifices some throughput for the long task. This is the same for all of the preemption mechanisms. Concord achieve lower throughput. We tested two configurations of Concord. The default configuration instruments at loops and function call. The other configuration has a more careful configuration, such as fine-tuning the depth of loop and rolling to reduce polling overhead. Even though our fine-tuning efforts, polling still wastes CPU cycles as the application has lower throughput. Our paper also includes another application for RocksDB, where user interrupts can also achieve over 50% of throughput. So we can draw a final conclusion. AspenKB with user interrupts can address the problem of head-of-line blocking in the microsecond scale workloads. To evaluate the AspenGo, we ran the application BadgerDB. This shows the performance of short task. The x-axis is still the load. The y-axis is still the tail latency. Lower is better. The conclusion is that even though our efforts in AspenGo, user interrupt still have limited benefits compared with AspenKB. There might be more potential benefits if more things are optimized, such as adopting a faster network stack like IOU ring. So finally, let's return back to the question we asked in the beginning of the presentation. Can user interrupts help achieve fine-grained preemption? Yeah, the answer is yes. User interrupts can address head-of-line blocking in microsecond scale. However, when one system is not fully optimized for the fine-grained preemption, the user interrupts provide limited benefits. Therefore, when using user interrupts on a complicated system, we still need a big change to the current software stack. Thanks for your attention, and I'm happy to take questions.